Good morning, everyone. Let's get started.
Good morning, ISACA members and guests. Welcome to today's webinar. I would like to introduce our guest speaker, Mr. Andrew Turpin. Andrew is the owner and director of Cybermint, and he was previously the Chief Operating Officer of Grindrod Bank Limited. Andrew has an extensive background in the financial services industry with subject matter expertise ranging from banking and payment systems to retail banking and general banking operations. Andrew is truly a techie at heart, and it is only fitting that his topic is everything as a code. Mr. Andrew Turpin, on behalf of the ISACA community, a warm welcome and over to you.
Thank you very much for that introduction. The topic this morning is everything as code, and it also happens to be the tagline for the company Cybermint, where I work. Appreciate the significance of that particular tagline. So let's dive straight in, shall we? Who does not like a good science fiction movie? I presume you all remember Tron from 1982, those of you who are old enough, or The Matrix from 1999, or the Avatar. I think the Avatar, I'm not sure if it was 2009 or 2006, but it was in that era. They're all good examples of how various means of virtualization were introduced through Hollywood into the mainstream consciousness. I remember as a youngster going to see, I was still in high school, going to see Tron and watching the light cycles and the virtual world of Tron, and completely blown away. It completely gave me a different view of the world. And this change in consciousness, which started in the 80s, has laid the foundation for the continual virtualization trend that we've seen from then and still continues now. And you see it in things today like software-defined networking, virtualized processes, containerization, and even virtualization right down to an individual function call. And we'll be talking about all of these things. And without that, we wouldn't have the cloud revolution that we have today. So let's move on then to talk a little bit about these ideas of velocity of change. I presume you all know who Berners-Lee was, the inventor of the internet. And he, in his mind, Web 1.0 was a read-only web. But since then, we've got a deeper understanding of the different phases of evolution that we've been going through. And this is going to be important because it frames the way that we think about the pace of change, or the nonlinear pace of change. So Web 0.0, we refer to the days of ARPA, the ARPA network, in the mid 70s. Web 1.0, the static web, and this is the internet that led to the dot-com boom of the 2000s. This is IOL online and so on, if those of you can remember the 2000s and the dot-com boom. And some of you will be old enough to have lost some money in that time when everything crashed, just like it's done recently. Web 2.0 is more recent, and we know this as the web of experience, or the experience web. It's all about the consumer, and this is what gave rise to the digital world that we're living in now. Web 3.0 is where we currently reside in this evolution of the internet. And we talk about the interactive web. This is the world of machine learning, of virtual reality and Internet of Things. And this is a far more interactive experience that we have in our interconnectedness with each other and with the machines around us. But this curve goes beyond where we are today. It goes to Web 4.0, which we know as the intelligent web. And it goes to Web 5.0, which I'll refer to as the conscious web, or as some have referred to it, as when we reach the singularity. I'm not making any predictions about the future, whether we are actually ever going to reach the singularity. The singularity is where machines become intelligent. But what's important about this development is it's non-linear. Another place where we see this non-linear type curve is in the technology adoption, and I've taken this graph of technology adoption by households in the United States. And whoops, just give me a sec. What we see from this curve is 4 or 5 interesting things from this graph. What we see is that the technology adoption by consumers, this is a consumer adoption chart, businesses is very similar, is that it's exponential in the beginning. So here, for example, on microwaves, we see it's an exponential adoption. What we also see from this, and it's very important later in our conversation this morning, is that older technologies are not totally replaced by newer technologies, although their adoption flattens off. In other words, radio hasn't disappeared because we have television, and television hasn't disappeared because we have YouTube and the internet, etc., but the adoption has flattened off. And this is very important. The best example of this is like steam. We don't unlearn an invention or a technology. We still have steam. Steam still has uses in specific industrial instances, but we use electricity instead of steam these days. Okay, the other thing to notice about this curve is it's actually an S curve. So the first part is exponential, and each new one is exponential, and the last part is an S curve. And one of the things that I want to raise here is this idea of a hype wave. You've all heard a motor car approach you, or not recently. In lockdown, we haven't heard many motor cars, but you've all heard a motor car approach you, and as the sound comes towards you, the compression of that sound creates a distinctive tone, and as it goes past you, the expansion of the wave as it recedes away from you, the tone changes. And in the memes of society, we also have these hype waves. So we were hearing about virtual reality and Internet of Things and machine learning long before they became commonplace. But by the time we hear the sound receding, we've already passed the inflection point. It's already happened. And that's what it is like with a lot of technology, including what we're going to be talking about today, which is all driven by virtualization. And this is all going to form part of the picture we're going to get to in the next slide. So let's go to the next slide. I thought I'd take a nice old map. This is what the world looked like in the late 1960s. Sorry, in the late 1690s. Right. The first thing that we need to give some thought to is that we are living in exponential time. So it's not just that the adoption of technology is exponential, but that the production of technology is exponential. And because the production of technology is exponential, the next iteration of the technology that we rely on or use comes at us faster and faster and faster, and so it goes. And there's more and more of it because there's more and more people doing it simultaneously. And this becomes a self-fulfilling experience, this issue of exponential time. And yeah, you feel it when you look around and you see how quickly everything's changing, and how much there is to learn and to keep up to date with. You kind of feel overwhelmed sometimes, and that's because we're actually not living in linear time. We're living in exponential time. So and I think we need to keep that in the back of our minds when we come to defense mechanisms of how to cope with all this change. The second thing is we need to keep in mind why we behave the way that we do. My daughter says to me that she says, "Daddy, you always seem to break everything down into 2 things. It's either human nature or it's politics." Perhaps that's an oversimplification, but the aspect of human nature is a very important aspect in understanding why we do things. So, for example, why do people obviate controls that are in place in the organization? And if we focus on the fact that they are bypassing controls and not why they're bypassing the controls, I think we're missing a very important part of the picture. And a lot of that comes down to organizational DNA in our organizations, and a lot of that is derived from human nature. And I think that's also important when we look at this technology that we're going to be discussing today, everything is code. Then the third thing is, there's a sort of a derived demand that comes out of all of this, and that is that our users, our businesses, our business partners, consumers have an exponential expectation. So as technology grows exponentially, their expectations, our expectations, also grow exponentially. And in order to keep up with exponential expectations, we need to change the way that we think. We need to change the way that we work. Even what we're doing today is one of those examples where we're changing the way that we work. So I think with that background, this leads us into the phenomenon that we refer to as digital. If we let me just move on to that. So these days it's a buzzword. This is the hype curve that we hear or feel coming towards us. And in some respects, this is already here and possibly almost past us. So what is digital all about? So when people say, you know, they want to have digital business processes, or they want their business to go digital, what do they really mean? And it stems from those two bullets of Web 2.0, which is all about customer experience, putting the client first, where experience is everything. And I think that's definitely a key part of this idea of digital. Digital also means, however, that providers, and we see this in the fintech world, that providers don't try to do everything, but what they do is they form part of an ecosystem of service providers. And embedded in this idea is this idea of microservices or distributed service providers. And you see how something in society becomes part of the technology that we use. These memes find their way into our technology, and from our technology into our society. I think it's both directions. What we also see is that digital has forced us to use new technologies with aging infrastructure. So what we find is, because of these exponential expectations, we've got these legacy systems, and we need to carry on using them. We can't get rid of them, but we're forced to put new technology on top of the aging infrastructure. And sometimes you see people do this well, and sometimes they don't do it so well. I often refer to that as putting lipstick on the pig, when you make an old thing look like a new thing, but it's not really the case. So one of the things that digital does is it leads to changing business models, and that means that we have unbundling and rebundling of services. So because the boundary between services change, because we're part of an ecosystem now, because instead of putting the product first, we're putting the client first. All of these things lead to a rebundling of the services and service offerings that businesses are providing. And it's all enabled by new sets of technology, which we're going to get to in a minute. A very, very important aspect of all of this, and it's one of the underpinning ideas of everything as code, is that data becomes a new asset class. There is a whole conversation to be had here, but I'd like to just leave you with this idea that data is a new asset class. We need to think of data as something that is productive, and data that is sitting and not being used is unproductive, is an unproductive asset. And all the ideas that go with a productive versus an unproductive asset. Right. So those are some of the ideas that come out of the digital world. What has the regulatory response been to all of this? Well, I'm going to put down one thing, but I'm going to mention a few. In Europe, we've seen PSD2, even as recently as yesterday, in conversations between stakeholders and the intergovernmental fintech working group, there were requests from the industry to say, well, maybe we should have similar things as PSD2 in South Africa. And the Payment System Directive 2 is a European directive to say that consumers own their data, they should have access to their own data, and they should be allowed to provide other service providers access to the data that you hold. So if you're an insurance company and you hold data, my data, I'm allowed to give permission to another service provider access to my own data that you hold, and you have to provide an API to allow that to happen. And of course, that gives rise to GDPR and POPI and the types of protections around that data that need to occur. Another regulatory response, which is not on my slide, but is the idea of regulatory sandboxes. And this comes about because all of this change, this exponential change, is happening too fast for the regulator to keep up. Now, regulation never preceded innovation. It always followed on innovation. But if the pace of innovation is so fast and the pace of adoption is so fast, the regulator doesn't see it coming. They can't hear the hype curve. So by introducing sandboxes, gives them the opportunity to hear the hype curve. We've, in South Africa, we've just launched this intergovernmental sandbox, which I think is very, very innovative, and the only place in the world where it is a sandbox driven by multiple regulatory bodies in a single sandbox. Right, so this gives rise to the fintech world and moves us more into the Web 3.0 space. And also many of these fintechs are startups. And what do? Well, you can see the correlation. They offer personalized services, but to everyone. So they're putting the client first from the beginning, not putting their products first and then trying to make it client-centric afterwards. One of the challenges that the incumbents face is in response to these threats, they increase their rigidification. They become more rigid instead of more flexible. So, and that obviously is why change occurs. And in my view, this is not a bad thing. This is just the natural course of events. And when the startups become the incumbents, the next phase of startups will do the same. Include this picture here because it's a picture of the Luddites rising up against the factories and the machine overlords. And what's very interesting is that there are multiple responses to all this change. The one is that you can respond by rebelling against it and trying to break it down. But in the end, the Luddites lost. Technology always wins over, well, in this case, over labor. And that is because you cannot put the genie back in the bottle. Once the technology is developed and known, cannot be put, it's like toothpaste, it doesn't go back into the tube. So let's start to get a little bit more technical now. I just want to take a note of our time. We're doing all right here. We're about halfway through our time. We started a few minutes late, so we should be all right. And let's start to get a little bit technical to get to this idea of everything as code. So the first thing that we notice here is that we talk about software development. And what is software development? Well, it consists of code. We build some code, we compile it. The development process is very manual. And the analogy is the punch card. And some of you might have seen a picture like this that I'm showing in the bottom left here. This, in fact, is a weaving loom. And those punch cards are programs for how the loom needs to weave the carpets or curtains or whatever that it's weaving. And this is where the idea of computer punch cards came from. And so that's this idea of software. And I'm going to keep referring back to the punch card analogy because that's where it starts. And I want to refer to this type of work, which is programming these cards, as white collar work. And I'm just putting up Lady Ada Lovelace's name. Those of you who know will know why that's an important name. For the rest of you, Google is your friend. So the other half of it is that you need something for these punch cards to operate on, and that's the loom, or the bare metal, the tin, the servers, the data centers. And I've put in a picture here of the ENIAC computer. Again, Google is your friend. Go and Google ENIAC. And what we see about the machinists, or those that maintain these services, is that's becoming more and more, and it was always more blue-collar work. What is interesting in these examples, and I only realized after I had made these slides, is if you have a look at the three characters working on the machines, and if you have a look at the name of the person who I associated just instinctively with the programming of the loom of the machine, they're all female. And it's just an anecdotal observation that from the early days of computing, females were right there at the heart of it. And yet today it's viewed very much as a male-dominated sort of area of expertise. And I think sometimes we need to just be reminded about where some of these things come from. So that was just an anecdotal observation. We're going to start getting exponentially closer to our topic. These foundational ideas become important in a minute. And the first part is that the more things change, the more they stay the same. What happens is the ratio of these things change with time, as we saw in the adoption curve. So what we start to see is that development is becoming more an endeavor of intellectual effort, whilst operations is becoming more automated and more depersonalized. And so what you find is that this area is becoming more specialized, and there's a gap growing between this area of specialization and this area of machine automation. And that drives the gap that we see over here. But these things do not disappear. This does not disappear. All that's happening is that the ratio is changing. And over time, I believe there'll be a new curve where these people that do this intellectual effort will eventually be replaced by machines or bots. And they will be automated away, etc. As the levels of virtualization continue. So that's where we started. But what happens when we add a new technology? And the minute you introduce the idea of a network, things change completely. And the best example I can give you is that of the fax machine. Now, not all of you will even remember what a fax machine is or have heard the wonderful sound it used to make. But a fax machine has no utility if I only have one fax machine. But if two people have a fax machine, it suddenly has utility. If 5 people have a fax machine, it has high utility. But the utility of one fax machine is 0. And this is the amazing thing of network. And it doesn't matter what we're talking about, whether it's computer network, human network, social network, any kind of network, that is the utility of the network. And without networking, we wouldn't be able to achieve the virtualization that we've been able to achieve. So I'm going to move on from that idea now of how one technology completely unlocks and enables additional technologies. And that's why we cannot put the genie back in the bottle each time a new technology is developed. And then, of course, we get new ways of working. So each time this happens, we have to adapt. We as human beings adapt, we work differently, and we move into a new cycle. So virtualization becomes possible. And virtualization starts to change the way we work, and therefore the way we think about what we are doing and how we are working. It also introduces a new vocabulary. And one of the pieces of advice that I would give to those of you who are interested is to get hold of a sort of a dictionary of technical terms, or make your own lexicon. Because if you can master the vocabulary, you're halfway through mastering the topic. And I have found that a very, very useful way of going. And I'm going to introduce 2 new words into the conversation today, besides all the technical words you'll hear. And those 2 words are cattle and pets. And you're going to see how that becomes important in a minute. But before that, let's have a look. So virtualization becomes possible. Well, it does become possible if I push the right button. So let's try that again. Virtualization becomes possible. And now we're getting a little bit down and dirty, and we see that we have the idea of servers. They make use of disk storage. This is stuff we're all comfortable with. This is what we refer to as tin. And this tin hasn't gone away. It exists in the cloud data centers, it exists in your data centers at work, and it exists on the desktop that you're watching this web seminar from. But on top of that, the idea of a hypervisor was introduced, and there are different types, many different types of hypervisors. I've put just two of the main ones, VMware or KVM. And what a hypervisor does is it abstracts this hardware into a virtual hardware for machines that can now come on top of it. And that's where we introduced this concept of virtual machines. So in your IT environments, you will have virtual machines. They would still be running an operating system like you would have run on traditional servers, but they can be created and destroyed within seconds. They can be configured to run any number of applications, and they can run any number of operating systems. So this one is running, for example, a Windows operating system, and this one's running a Linux server operating system. And so there you see. But what a virtual machine does is there's no theoretically, in practice there is, because there's only a certain amount of resource that you can abstract from here into these machines. There's no limitation of how many I can have of these. And so what I can do is I can have a whole bunch of these virtual machines, each of them doing their own thing. Each of them looks like an entire computer. So it's not just a single application or just a database, it's an entire computer. It has a hardware abstraction, which comes from the hypervisor. It has an operating system, and then it has the applications that run on it. Each one of these boxes is an entire machine. All right. That means that each one of these things are different, similar to how each of your pets or children might be different. And that's going to become an important idea in a minute. So let's get to cattle and pets. That's what cattle looks like. I love this picture, actually. And that's what pets look like. And I love that picture, too. And I looked through here to see what was the same about each of these pets. And yeah, it was an interesting exercise. I couldn't find any pet that was exactly the same. So let's talk about cattle. So the interesting thing about cattle is we treat them all the same. We don't really give cattle names. They don't have friendly names. They don't require individual care. What they do is they require herd care. They are replaceable, albeit costly. You can replace one cow with another cow, and your herd remains intact. They sleep outside. We don't coddle them. They're fairly robust. If you know how to deal with one cow, you know how to deal with all cows, and so you deal at a herd level. Let's talk about pets. Well, the thing about pets is each one is different. Each one is unique. They each have a special name, although I wouldn't be able to remember so many names of all of these pets. They are actually irreplaceable. If you lose one pet, you cannot get it back again. Cannot be replicated. They are vulnerable and typically don't sleep outside, certainly not in winter. They require constant attention. It's a bit of a vicious cycle because the more we give them attention, the more attention they require. And that, in fact, is their purpose. It becomes their purpose. In other words, they encourage petting. They encourage the attention that we give them. And these distinctions become important when we look at how we start to deal with our IT infrastructure. So what are the implications? Well, in the normal virtual machine world, we sort of treat each virtual machine like a pet. And that is an expensive exercise. So we can try treating servers more like a class of pets. So these bunch of virtual machines are all Dachshunds, and these bunch of virtual machines are all, I don't even know all these dog species, but say Alsatian. One of the implications is that every service config is therefore different. For example, every DR for every server is likely to be different, even if it's from the same class of pet. And this has a further implication, because if you've got 190 of these things, well, then it doesn't scale. You start to have the situation where you have, if you have 100 servers, you have 100 discrete points of failure, you have 100 unique types of risk, and you have 100 set of complexities. And so treating your IT infrastructure like pets simply doesn't scale. Each server instance is never truly replaceable. This thing of encourage to petting means that what happens is that sysadmins log on to the infrastructure, they make changes, and and they don't really know what all those changes are, no matter how good your change management is. So if we think of virtual machines as our first level of virtualization, we can try and achieve some type of codification of that virtualization. We can use predefined templates to create virtual machines. It's often hypervisor specific. We're still very close to treating them like pets. We can keep the templates for those machines in a source code management repository, and we're going to talk a little bit more about source code management repository in a minute. I see there's a lot of activity on the group. I can't watch all the activity while we're speaking, but I definitely would like to get back to it. Each template needs individual configuration, and DR is best done on a machine-by-machine basis, so you would do machine replication. This is expensive because you're replicating an entire machine, not just the application or data that you want to replicate for DR. Software development now that is done in a virtual environment is often still done manually. There's a bunch of install scripts, but it's still done manually. And perhaps some ways of improving it could be using Jenkins to orchestrate deployments. But one of the biggest dangers is that configuration is often done manually on a machine-by-machine basis. And there are tools that one can use, like Ansible, which we'll have a look at in a minute, to try and improve that. And this is where we start to get more and more into this idea of everything as code. And I'm going to introduce some new vocabulary. Ansible is an example of an idempotent stateful change management tool. And what that means is, what idempotent means is, if I apply a set of changes and I reapply them, the state of my server or my application configuration is the same. In other words, if I say that it must have this configuration and I apply it, and then later I reapply it, I know that it has that configuration. Because you do get non-idempotent types of scripts where if you run it, you end up with a different state than you had after the first time if you rerun it after the first time you had it. Okay, so we've introduced a whole bunch of new ideas and new concepts here. But the issue about configuration on virtual machines is that we need to start moving away from treating them as pets and start moving towards treating them as cattle. And that means using tools like Ansible, like Puppet, to achieve idempotent stateful change management. All right. Well, there's some cons with just using virtual machines. Each virtual machine is a full machine. So, thanks. So let's carry on. So other issues around running things in virtual machines is that it's hard to do network abstraction. You still bind virtual machines to physical network interfaces. If you want to, and often what happens is if you need to reboot a server because an internet server, for example, is not working, you have to reboot the machine. That means that all the applications on that virtual machine would be rebooted. So it has a potential overflow to the other applications running on that virtual machine. So these are some of the cons of virtual machines. But we can template virtual machines, and templating virtual machines gives us the first abstraction, which is machines as code. And scripting the configuration files for those virtual machines gives us the next abstraction, which is configuration as code. And there, the ideal type of configuration needs to be stateful and idempotent. Right, so here's an example. I'm not going to go into too much detail, but the reason I'm putting the example here is when I say everything is code, here's a real example of provisioning machine as code. And this is one that I ran on my machine to test it. And you can see that I'm doing a virt install. This happens to be for KVM. Looks very, very similar if it's other hypervisors. And I'm creating a machine that has got 2 CPUs. So there you can see 2 CPUs. I've got 30 gigs of hard drive. I'm running a 64-bit server on there. And my network, I'm connecting to this virtual network here, this software-defined network bridge. And this is your machine. I can keep this definition in my source code management. If I need to change this, I can track changes to the definition of this machine. I can make sure that the image that I'm using to build this machine, this virtual machine, is one of my hardened images, for example, etc. And then when I create instances of this machine, they are identical based on this definition. So that is provisioning machine as code. If we go to configuration, I've given an example Ansible playbook, and you can just peruse through this, and it's really just a set of declarations. This is what is known as stateful configuration. It's a set of declarations to say this is what the config should look like. And I want to just highlight for you here at the bottom under install packages, where it says make sure that your package repository is updated and install the required system packages, and there's a variable that gives a list of what is required, and then make sure it always has the latest. And down here, UFW is an uncomplicated firewall. Make sure that you allow SSH and deny everything else. Now, no matter what the configuration is of my machine, if I apply this config, then this is what it's going to look like. And everything else would have gone away, and it will look like this. And so this is an example of declarative and idempotent approach, which means applying and reapplying always leaves the machine in the same state. It has been declared to be so. Okay, I'm gonna move on. The next level of abstraction that comes from in the virtual world is that we need to glue all of these things together. And what I have here in front of me is a picture of a pipeline, a continuous integration pipeline. We use an orchestration tool, and there's many different orchestration tools, Circle CI, Jenkins, etc. And what it does is it allows you to configure the pipeline for your environments as code. So it shows how you would integrate your source code management, what your build operations would be, what code analysis you might do, what regression testing you might apply to your APIs, what archiving of binary artifacts and build artifacts you might do, and where you might pull binary artifacts from, what integration deployments you do, what integration instances you need to deploy, for example, into the cloud or on-premise, and then a bunch of testing. And at the testing level, all the things that are music to your ears: integration testing, performance testing, and security testing. But it can extend beyond that. So, for example, you can get things like security as code, configuration management here with Ansible, etc., and even documentation as code, which we'll get to in a minute. So that's what a typical pipeline as code might look like. So the next time you see something like this, then you can get an idea that it forms part of this philosophy of everything as code. So a discussion on everything as code is not meaningful without talking about source code management. And your source code management effectively becomes change management as code. So here, for example, is a little open source project that runs ping tests, and you can see all the changes that have occurred, and some change was made. There's a change reference here. It's called a commit ID. But what source code management, and this just happens to be GitHub, but there's lots and lots of different source code management tools. What it does for you, though, is it allows you to keep track of the change management. So, for example, this commit, this B316623, this commit here, this is what changed. And you can see when the change occurred and what was added and what was deleted. In this case, it was just a small thing to change something. But this is an example of how everything in your source code management is self-documenting with respect to change management. And when we live in the world of everything as code, then your source code management tool is fundamental. It's one of the foundational tools that you would have in that environment. All right. But what happens if we say we don't want a machine as code only, but we want to make our application and our services and bundle them as code? And that's where containerization comes in. This is a real Docker file. It's not complex, and I've put it up there for you to just have a look at it. I'll point out one or two things in a minute. But what containerization does is it takes this idea, this virtualization abstraction, another level, and it says, well, instead of just abstracting my virtual machine, let me also abstract my code and my service into a container. And by doing that, I decouple my service from my environment. So if I kill my application, I don't have to reboot my service or my server. So here you'll see there's a container. This is the definition for that container. And I just want to point out just two or three things. The first thing is that this definition tells me how to configure my container, what it's based on. It tells me what to do once I've configured my container. So here I must install a key server. Here I must add in file paths for my logs and my errors. And here I must expose on my container just these two ports. This changes the way that we look at an application, because a container now only exposes the thing that it does. Typically single purpose. This is running an Nginx web server as a daemon, and it only exposes port 80, which is your HTTP port, and port 443, which is your TLS, your HTTPS port, your secure web port. What you notice on the left-hand side is that nothing's gone away. You still have your hardware disk arrays, you still have your server, you still have your hypervisor, you still have virtual machines, but now you have another level of abstraction, which is your Docker services, and then all your Docker applications. So that's the next level of virtualization or of abstraction in the virtual world, but it doesn't stop there. Once you have Docker containers, these Docker containers can be composed into a system as code. So we started off with a machine as code. We then went on to configuration as code. We then went on to a system or service as code. But you can compose services. You can compose services into a system as code. And here's an example of a Docker compose file that composes these three Docker components: a proxy server, an application, and a database. It builds software-defined networks, one called backend and one called frontend, to glue these things together, and it exposes only one port to the outside world, to this entire service. And this is a legitimate Docker compose file, and it's very, very easy. And this is now an entire system as code. And so what you're seeing is you're seeing an additional level of abstraction. But as the telemarketing salesperson says, and that's not all, it doesn't end there. So what's the next level of abstraction? Well, the next level of abstraction is to do an entire data center as code, an entire cluster. And if we did an entire cluster as code, what we end up is something that looks like this. Now, there are different types of container orchestration solutions. that would allow you to do this level of abstraction. I'm only really familiar with Kubernetes, but I know that there are others. But this appears to be the mainstream technology, and probably the one that's being used in your environments. And it's the terminology here is what you would need to learn in order to be able to understand what's happening in this environment. So what we have now is we have your entire data center, this box here, which is your virtual description of your data center as code. Now, this gets a little bit complex, but what we can define here is all those systems as code are defined and how they interact with each other and the various nodes that they're going to run on and the monitoring for those nodes and the virtual networks that link all of those nodes are all defined at this level of abstraction. So in order to do that, we get the configuration for your data center as code, like Ansible was your configuration for your virtual machine or your application as code. Helm becomes your configuration or your package manager for your data center as code. And it's a little bit complex, so I didn't go into it in too detail, but Helm is a collection of definitions, again, which are all kept in source code management, which define how to build your data center infrastructure as code. And if you just look at the names of some of these things like services and ingress, which is how you get in and out of something, and your charts, etc., this gives you a clue of what you're doing. But the important thing is that not only do we have a package manager for our infrastructure, but we have a supervisor in Helm to ensure that the infrastructure is what I say it is. So here's the example. I would have a Helm chart that says, create me these 3 services or these 4 services, and it must always look like that. So if, for example, one of the services crashed, what Helm would do and what Kubernetes would do with the Helm definition is say, one of these services has gone down, I'm going to recreate it and reinstantiate it. And so you have a stateful definition for your infrastructure. Whereas before we had a stateful definition for our config, we now have a stateful definition for our infrastructure. Another example that it can do is I can say, optimize this infrastructure so that there's always enough resources for each of the services running. And I say that's the behavior that I want my infrastructure to exhibit. Now, a particular node becomes too busy because there's other things happening. Helm, not Helm, but Kubernetes, because of the instruction that was given, would move a service from that node and put it on a different node so that it had more resources and it met the requirement that I gave. When I defined my infrastructure, I said, make sure that you have this amount of resource, or make sure that you have this affinity, that these 2 services always need to be close to each other, wherever you put them in the environment. And so that's another level of virtualization or abstraction. Right. Again, I highlight that nothing's gone away. We've still got the steam engine. We've got the loom down here. But the sophistication of our punch cards has increased exponentially as we go. Right, we sort of coming into the end. And so everything is code. Even your documentation can be code. You can have a living wiki instead of Word documents. The problem with Word documents is people version them, they file them away, and then they get out of date. That doesn't serve the business. It doesn't serve any of your control objectives. It really is just a waste of human enterprise and energy. But using a wiki for your documentation means that the wiki becomes a living thing. As things change, you change it. It's instantly available to everyone. And a wiki is just an example. I'm talking about using living documents instead of static documents. But other things can be code as well. So we get design as code. Some of you, I mean, all of you have heard of APIs, I'm sure. But in the RESTful world, there's examples of something called Swagger. And what Swagger does is allow you to define your APIs as code. And from that, even automatically generate a large portion of the source code for implementing those APIs. We've spoken about Jenkins and orchestration as code. I'm going to talk a little bit about testing, and the one example I want to use here is this example here on the right. What you see here is a definition for testing, and it's saying go and run this test, go and do an attack for open ports, and the only port that should be open is this telnet port. Any other port shouldn't be open, and you can include this test, which is code, in your source code repository, manage changes to your test, and they become part of your pipeline. And on the left, I have a little example here of design as code. Here you have a state diagram. So for example, and it's arbitrary, everyone's got a different view of how this state diagram might look. So you start in a state of FICA pending, and then you can go approved or back to pending, or you can go to expired, etc. But that state, however you design that state, can be declared in code like this, for example. And so we need to think a little bit differently and say everything can be thought of as code. Right. What about access control, permissions, and security? So I've been doing some work that I started a while ago, and open source work. I architected a solution for security as code. And here you have, for example, a security contract for an application, and it maps permissions to functions. And you can see here that this permission has the permission to read, and it's part of this user's general function to access something in that system. And this is also a stateful view of security, because if I reapply it, whatever the security was, this security contract forces it back to this view. So even security can be treated as code. What does this mean? Well, this means that DevOps becomes a legitimate citizen in your enterprise environment. So you used to have on the left-hand side, and please excuse the hardy-do, it's sitting right outside my window, and I don't have a way to chase it away. On the left-hand side of your organization, you have your sysops or your sysadmins, and on the right-hand side, you had your developers, and there was this hard boundary between them. And we developed and maintained our controls, our audit practices, our governance, everything around this hard boundary. But when you move to the world of everything as code, then what you have is disciplines that are that cross across the organization. You don't have hard boundaries anymore. And so you need to revise all of those approaches. And DevOps has now become a legitimate citizen in our corporate environments. Some vocabulary that I've already mentioned, but I just want to highlight is this idea of continuous integration and continuous deployment. Continuous integration is getting your code building and testing and so on. Continuous deployment is being able to deploy to multiple places and multiple instances in a day into your production environment continuously. I see some people are leaving because we're running out of time. I apologize, we started a bit late. We'll finish at about 1:15. The distinction between cloud and on-premise starts to disappear when we start talking about everything as code. And we start working with this idea of reproducible resilience. Because I don't have to follow a set of instructions to rebuild a server. I apply the code that defines how that server works, or how that system works, or how that data center works. So, and it can be applied to all the source code artifacts. Right, but what about, I've only spoken about the good things. The caveat emptor, let's have a look. Exponential time implies an exponential rate of knowledge growth, which in turn implies an exponential complexity, which in turn implies automate or die. And by die here, I mean is if you start utilizing these technologies and these philosophies in your business and you don't automate, then you will not be able to keep up. And you will collapse under the burden of the complexity. So increasing complexity is not reduced with everything as code. We can't avoid the increasing complexity, but it is abstracted or demystified. Nothing in the code definitions that I showed you were that that couldn't be demystified. But for us as professionals in this space, there's no way around learning it. And my view is start by learning the vocabulary. Not everyone needs to be a developer, everyone needs to be a DevOps expert. But by learning the vocabulary, we can demystify this complexity to a great degree. If we need to change the way that we approach risk management, if we approach it with the loom and punch card thinking, then we're going to end up being irrelevant, and it's going to lead to conflict between governance and audit and risk professionals with developers, DevOps, and sysops. So we actually need to change the way that we think about risk and our risk frameworks. Can't just reformat them. And then the sad truth is there is no silver bullet. There is never a silver bullet. There is only where we are today and where we will be tomorrow. So what I'm going to do is I want to come to the end and then offer some opportunity for asking questions on the chat. So if you can start posting your questions on the chat, then I'll answer them as soon as I'm finished the slide. But there are certain implications about key controls. The first is keys, secrets, and access. This is complex, and these are the things that you need to think about. You need to think about authentication, authorization, auditing, and asset permissions in your security realms. And this works differently in a world of everything as code. The next thing is that we need to realize that DevOps tools enforce processes and are self-documenting. That means that creating an expectation where the DevOps and the developers need to do additional documentation is unreasonable. What we need to do is learn to read the code that the tools generate. Change management is source code management. If you're going to understand change management, then in this environment, you need to learn your source code management tool. And I would suggest learning your way around Git. And again, start with the basics. Logs. And this is going to become important because in this environment, what we do is we manage exceptions, and without logs, and all of this produces logs. One of the side effects of this change, where everything is defined on a punch card and not in the loom, is that your developers and your DevOps become more critical, more powerful in your environment. And a key form of control is peer review. It's always been true. A developer can put anything in the code that gets put into production. So peer review becomes more and more important when everything becomes code. I've raised this twice already before, but complexity is an invidious enemy. And you need to make sure that in your environments, everybody is challenging unnecessary complexity. You can't tack on security at the end. You have to integrate security into everything. And this is a whole topic on its own, so I'm not going to be talking about that. Living documentation I've mentioned. And the fact that DevOps, or everything as code, is not silo bound. It cuts across the organization. So we need to look at segregation of duties in a different way. And continuous integration and continuous deployment increases deployment velocity. So you cannot, for example, audit every instance of something. You have to look at the definitions in the code, and then you have to become exceptions focused as things become faster and faster. The tools are often driven by open source, and you need to take some time to learn your way around the open source world. And transparency is always better. This is more a philosophical response to all of these things. But if everything is code, then everything can be peer reviewed, from designs, business documentation, code deployments, infrastructure testing, change management. So my view is take the time to learn your source code management, take the time to get familiar with the various tools in the tool chains. So things I haven't mentioned is skills matter more than tools. Tools matter more than effort. Dependency is always a problem. Always use trusted sources. Training. There's a whole bunch of other topics and ideas that come out as implications of what I've just spoken about this morning. So, and what I'm going to do is I'm going to shift back now to answer questions. Let me bring the chat into view in a second. Everything as code means that everything becomes continuous. And that means that we are going to be rethinking how we work and how we interact with our means of production into the future. So thank you very much, everyone.